video on drawing resonance structures and calculating bond order. Well, in some molecules and ions, resonance occurs when bonding can be represented by just one single Lewis structure. So they will have more than one valid Lewis structure, meaning two or more possible Lewis structures or Lewis formulas for single molecule or ion, and that's where that is called the resonance structures. So they are still, all of the structures are valid, but they are not true. They don't actually exist in nature. And however, they still help us, resonance structures still help us in finding the actual resonance hybrid and actual structure. Well, calculating bond order. Okay, so here is the definition. Number of chemical bonds between a pair of atoms is the definition for the bond order. How do we calculate it? We use this formula. We write total number of bonds in the numerator and location of bonds in the denominator. So why are they even important? So first one, the resonance actually results in delocalization of electrons. So delocalization is a keyword. It's an extremely important word when you talk about resonance, because it's all about the delocalization that makes it more stable. So electrons are not at one position, they're not fixed around the atom or on atom or in the bond. Actually they're everywhere, like they are going to spread themselves. And more is the resonance, more is the stability. So they are directly proportional. Same thing, higher is the bond order, more is the stability of the molecules. So as a result of delocalization, energy of the molecule decreases, and lower is the energy, more is the stability. Let me take an example of, here, let me do it here. Okay, ozone, which is actually an allotrope of oxygen, O3. So let's follow the rules for Lewis dot structures. We're going to start. So if you don't remember the rules, please review the rules for the Lewis dot structures. Oxygen is 6 valence electrons, and since you have 3 atoms, you are going to write here 3. And 6 times 3 will be total 3 valence electrons. And remember, we are dealing only with the valence electrons when we draw Lewis dot structures. So in order to show these electrons, so I'm going to use all these electrons here for the Lewis dot structure. I'm going to start. So the rule says first you need to distribute these electrons, making sure that you have a single bond in between each of the atoms, the pair. So I have used 1, 2, 3 and 4. How many are left now? Out of 18, I have 14 more. So I'm going to start distributing rest of the 14 electrons in such a way that octet of, starting from the terminal atoms, their octet is complete. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and I said 14, so here 14. Okay, now let's see the octet of each one is complete or not, because it's all about completing the octet that results in stability. So here 8, 1, 2, 3, 4, 5, 6, 7, 8. Here 1, 2, 3, 4, 5, 6, 7, 8. Here I have 1, 2, 3, 4, 5, 6 electrons only. So what do I have to do? So this one has the incomplete octet, right? Incomplete octet. To make the complete octet for this oxygen, I'm going to move this lone pair. Well, this one or this one, like which one? So when we move this lone pair and change it into a bonding pair, you will have a double bond here. But again, which one? So there are 2 possibilities. I can have the double bond. So here, let me keep the number of electrons same. We don't change the number of electrons, guys. So here's, if I move this pair, this will be the double bond here. I'm going to keep this one single bond. And if I move this lone pair, then I will have a double bond here. Okay. So please make sure that overall number of electrons are not changing. They remains the same. Okay, with the double bond you have only 2 lone pairs, and with the single bond you have 3 lone pairs, because one of the lone pair is used here. Now both these structures are correct. And actually, they are valid because they are satisfying the octet of each of these atoms. 1, 2, 3, 4, 5, 6, 7, 8. All right. 1, 2, 3, 4, 5, 6, 7, and 8. And then 1, 2, 3, 4, 5, 6, 7, 8. So octet of each one is satisfied. Guys, you remember for one bond we need 2 electrons. But they don't exist in real life. Actually, we draw this double-headed arrow in the middle, and this double-headed arrow will show that none of these are the real structures. These are imaginary. These are hypothetical. So you are going to show here the mixture, the intermediate structure of these two, and that is how you're going to draw that. So you're going to draw this bond as a dotted line, which is actually showing indicating the possible location of the double bond. All right, and you can see it is showing that it can be anywhere, 2 locations. It could be here or here. Like instead of saying double bond and single bond, now you see how it is spreaded, how it is delocalized. So here, this is called the resonance hybrid. Resonance hybrid. And this is the actual structure in real life. That's how the ozone molecule would be, not like these. Well, we still need these because these structures are helping us in describing the actual structure. Now, what is similar about these resonating structures is the number of atoms, the number of electrons are same. And what are we changing here? Well, we change the location of the arrangement of electrons, right? However, we didn't change the position. We changed the location of electrons, but not the location of atoms, meaning the skeletal structure is still the same. All right, so let me see, we covered everything. All right, and we talked about the delocalization. So delocalization, higher is the D, more is the delocalization, less is the energy, okay, and higher is the stability. More delocalization, low energy, higher stability. So that's the relationship between these three. And what else? Okay, so let's figure out the bond order because we are also working on the bond order. Bond order, we said the formula for bond order is we look at the total bonds and the location. So total bonds we have 3, 1, 2, 3, and the location, as we said, it could be either here or here, and that's what it says here. It could be either here or here, so 2 locations. So you have 3 over 2, which is 1.5. Okay. Don't forget that. And let me do one more example actually. This example is not bad. It's good. It's a good example. Nitrate here, you have, it's a little different, and it's a good example. So again, we have to write the total number of valence electrons, 5 coming from nitrogen, 6 coming from oxygen, 3 is the number of atoms, 1 is coming from here. So total number of electrons are 24. Let's draw the Lewis dot structure for this one. 1, 2, 24, 3, 4, 5, 6, just making sure we have at least one single bond in between. And then how many are left? You have 18 more left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So here the octet for this one is complete, for this one is complete, this oxygen complete. Well, this center nitrogen, we have this nitrogen in the middle because that is less electronegative than oxygen. The more electronegative atoms are around it. So here nitrogen is the central atom, well, because it is less electronegative. That goes back to the rules of writing Lewis dot structures. Well, here we are just focusing on the complete octet. So this one is not complete. Here we're going to do the same thing what we did earlier. we are going to move the lone pair and change it into the bonding pair. So where the double bond will go? Here, here, or here? Well, it can go anywhere, right? It will go, let's say, okay, let's say we have a double bond here. We decided to move this. We have to start from somewhere. So if we move this lone pair here, we will have a double bond here, right? And since I use one lone pair to make the double bond, I have only two lone pairs left here. The rest of them will have three lone pairs of electrons. Okay, well, but then as there are three atoms of oxygen, so we have three possibilities of having the double bonds. So three locations, one here, and now if I decide to move these electrons here, then I have to make sure that these bonding electrons, so these electrons from the pi bond, we have to break. So pi bond, they break and they are placed back here. They're pushed back because you want to make sure you're not making any expanded notation, expanded octet or anything. Here you want to make sure you have 8 valence electrons. So you are going to, because you want to make a double bond here, you have to push this one back. So this one will now be the double, okay, but then this one becomes single. 1, 2, 3, 4, 5, 6, and here I will have these two pairs only. Now the next one, all right, so what do we want? Oh, okay, here oxygen. What do we want? Here 1, 2, 3, 4, 5, 6. Here is the single bond, single bond, single bond, single bond, here double bond and double bond. So what you are doing here is, if you decide to have a double bond here, you're going to move this lone pair over here, and when you move that lone pair over here, you will have to again break this pi electrons from this pi bond and bring them over here. And as a result, what will happen, you will have a double bond here, okay? And because you have a double bond here, meaning that lone pair was moved over there, used in making that bond, you will have only two lone pairs of electrons. And this one will remain single. So all this is showing is that the location of the double bond can be anywhere. And it will go back. If you decide to move this, then you will have to put these electrons back from the pi bond. I'm going to put the double-headed arrow, and once again please keep in mind that when you're making these double bonds, here, here, anywhere, doesn't matter where, they are all making sure that the octet for this central atom is complete. Remember in the beginning that was the problem, that we didn't have a complete octet for the central atom. By having this double bond or moving the lone pair and making a bond, our central atom, the octet is complete as well. Just put them, just remember to put these brackets because you want to show that the charge is spreaded, and put the negative charge, that charge, because it's spreaded for all atoms. And here, don't forget to put the double-headed arrow, because double-headed arrow means that actual structure is none of these. Actual structure is the hybrid mixture of all these. So I'm going to draw it here. Let me draw this here. You will have nitrogen in the middle, right? Oxygen, oxygen, oxygen. So what you're going to do is, you have these full single bonds, but the fourth one here, you're going to show it by the dotted line. That shows that it is spreaded. It is delocalized. All right, so you did not change the number of electrons, you have just changed the location of electrons. Here this charge is again spreaded, and yes, we have that, and double bond it has satisfied the octet. Well, what is left? So here, this again, the dotted line is showing that possible location of the double bond here, here, here. So there are three possible locations. So that's how we figure out the bond order. And the bond order will be, going to look at the total number of bonds. We have 1, 2, 3, and 4. 4 total bonds. And then, or you can say here 1, 2, 3, and the fourth one, you see how that is shown by the dotted line. And 3 locations right here. 1.33 is the bond order. Okay, now I want you to try this one on your own. And for the nitrite ion, just look at the one you have, the examples you did, and then please double check everything. I have written all the notes for you. If you miss anything, please read, go back. Well, but I have written all main important things here. And here too, I want you to try this one as well for the carbonate ion. I have everything written here for you. So please, if you still have problem, and I have shown you the movement of lone pairs and how the bonding pairs are put back to lone pairs. Okay, now here is your turn. Again, read these. I want you to read all of these, and I want you to write the answers if they are true or false. All right, so pause the video. Well, all these statements are true. It's kind of a summary. It's like a quick notes. And I hope this explanation was helpful. So guys, this is a complex topic, but I have covered the basics, very, very basics, so that you can understand the complex one. But for Gen Chem, this should be good enough. All right, hope the video was helpful. Thank you for watching.